So here's a fun little problem on the 2025 American Invitational Mathematics Examination, specifically problem 10 on the AIME 1. We have ourselves a 3x9 grid, and we want to fill it with the numbers 1 through 9. Each row has 9 different numbers, and each of the 3x3 blocks, which I've outlined heavily below, also contains 9 different numbers. Basically, it's like a Sudoku puzzle, and we're trying to find how many ways can we fill this grid. Okay, let's think about this. First, notice something really cool. For the numbers 1 through 9, we can actually swap them around without breaking anything. For example, if we replace all the 1s with 2s and all the 2s with 1s, the grid is still valid. And that's because all the numbers are totally symmetric. And this observation will save us a ton of work later. So let's start with a 3/3 square. To make things easy for us, let's fill it with 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, here's our plan. Let's count the number of outcomes given this starting combination and then multiply by the number of possible starting combinations, which is obviously 9 factorial, since there are 9 factorial ways to arrange those first numbers in that 3x3 square. Now, here's another key observation. Within each 1x3 row in any 3x3 block, the numbers can then be rearranged freely. And why is that? Well, swapping those 3 numbers is never going to break any rules. That means that there are 3 factorial or 6 ways to arrange them. So really, we just need to figure out which 3 number groups go where and then multiply by 9 factorial times 6 to the 6 to account for all arrangements. Alright, now let's look at the first row of the second 3x3 square. What numbers can possibly go here? Well, it has to be some combination of 4, 5, 6, 7, 8, and 9. So let's just try something and call it case 1. First, pick 4, 5, 6, and let's see what happens next. So what exactly happens next? The second row has to be 7, 8, 9, because the third row can't include any of those numbers, since 7, 8, and 9 are already there in the third row. And guess what? If we had picked 7, 8, 9 first instead of 4, 5, 6, it's essentially the same scenario, just mirrored. So we can just multiply by 2 to account for both situations. Now, you may ask, what about the third row of the second square? And let me tell you some good news. Since we don't need to worry about anything, we don't need to worry about the last row of the second square since it's automatically determined. It's just going to contain the 3 numbers that we didn't pick. And even better, that fills out entirely for the third square. So for case 1, we have just 2 times 1, or 2 unordered combinations. Nice! But anyways, let's move on to case 2, where the first row of the second square is not 4, 5, 6, or 7, 8, 9. That means we'll have either 1 or 2 numbers from the second row of the first square, and the rest from the third row. And again, by symmetry, it doesn't matter which is which, so we'll just assume we're picking 2 from the second row and 1 from the third row, and then multiply by 2 later. So how many ways are there to choose a starting row for the second square? Well, there are 3 ways to choose 2 numbers from 4, 5, 6, and 3 ways to choose 1 number from 7, 8, 9. And let's pick 4, 6, 8, just for demonstration. Now, the second row has some restrictions. Which numbers can't go in there? That will be 4, 5, 6, and 8, since they're already either in the same row or in the 3x3 square. So that leaves us with 1, 2, 3, 7, and 9 as possibilities. So does that mean we can just go willy-nilly and slap in whatever numbers we want out of these 5 choices? Unfortunately, no. In this case, both 7 and 9 must absolutely be included. Otherwise, the third row would end up taking 7 or 9, which is a big no-no since it's already there. So really, we're choosing 1 additional number from 1, 2, and 3, which gives us 3 options. Let's pick 1, 7, and 9, again, for demonstration purposes. Then the third row and the whole third square are automatically filled with the remaining numbers. And counting all possibilities for case 2, we get 2 times 3 times 3 times 3, which equals 54 combinations. But don't forget, this is just for one choice of starting squares, and they're all unordered triples. We have 6 1/3 strips in the second and third squares that can be rearranged in 6 ways, and 9 factorial ways to choose the first square. So the total number of ordered outcomes is 9 factorial times 6 to the 6 times 54 plus 2, or 56. And then we can break down each term into its prime factorization. So 9 factorial is 2 to the 7th times 3 to the 4th times 5 times 7. 6 to the 6th is 2 to the 6th times 3 to the 6th. And 56 is 2 to the 3rd times 7. You can combine all the powers, and we can get a grand total of 2 to the 16 times 3 to the 10 times 5 times 7 squared. And that's the number of ways to fill in the board. But not so fast. The problem is asking for the sum of P times A, Q times B, R times C, and S times D. So we just gotta add up all the products of the primes and the exponents. In other words, 2 times 16 plus 3 times 10 plus 5 plus 7 times 2. And there we have it. The final answer is 81, and we're done.